Hello and welcome to York Observatory's monthly TeleTube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, and alumni and friends of York University. We are broadcasting live from the Alani Castle Observatory located at York University in Toronto, Ontario, Canada. York YouTube broadcasts every last Friday of the month at 7:30 p.m. local Toronto time. For any questions or comments you have about our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always contact us on Instagram at York Observatory, on Facebook at Alani Caswell Obs, and we are now on PixelFed at Alani Caswell Observatory. We would like to inform you about the opening and call for applications for the summer 2025 Astronomer in Residence program. This program is a collaboration of the Alani Caswell Observatory with the Killarney Provincial Park to host astronomers in the certified dark sky site of Killarney, where they will lead in-person presentations and shows using the park's observatory. To learn more about the program and its requirements and the application process, visit our website at yorku.ca/science/observatory/air. Good evening, everyone. I am Denelle, and I'll be one of your hosts this evening, along with Darius, Dev, Hector, and Zach. We are here from the Alani Castle Observatory at York University. Tonight, we have a great presentation about the validation of stellar chemistry machine learning models. The observatory at York campus is in Toronto. We would like to welcome you to the show and to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many Indigenous nations. The area known as Takaranto has been caretaken by the Anishinaabe Nation, the Haudenosaunee Confederacy, the Huron-Wendat, and the Métis. It is now home to many Indigenous peoples. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. Our stargazing and astronomical efforts join the long history and current practices of astronomy in this land. The observatory looks forward to continuing to learn and revitalizing knowledge in this area. With that, I will hand it over to Darius to tell us what's up in the sky this week.
Welcome, everyone. Before we get started with our main show, we want to give you a little update on what you can see this coming week. This week, we have nearly all the planets visible to observers in our area. At the time of the show, both Jupiter and Mars are up in the southeast sky, easily visible to the unaided eye. Venus is also visible, though it will be setting soon around 9:30. Don't fret if you miss it though, just look southwest after sunset sometime in the coming days. The outfielders Neptune and Uranus are also visible in the southeast sky, though both require some sort of observing aid to spot. Whether that be powerful binoculars or your own telescope, we wish you luck in your endeavors. To those who reside far from the city, or have more powerful gear, Andromeda currently lies west and should be visible until around 2 a.m. Be sure to catch a glimpse at our closest galactic neighbor, as it is the easiest galaxy beyond ours to see in the night sky. It's not a good observing time for fans of the moon, as it sets around 8 and is fresh into its waxing crescent phase, so it's hardly visible. However, this means slightly better observing conditions for the stargazers among us, since it results in a darker sky. Significant stars to look out for include Betelgeuse, a red supergiant star that is nearing the end of its lifespan and has a distinct reddish hue. Search for the Orion constellation in the southeast sky, then pinpoint the red star to the up and left of the belt. Also look for Sirius, the brightest star in the sky, excluding the sun. Look southeast at a low altitude, with its close proximity to Earth of only 2.6 parsecs and its naturally high luminosity. Sirius has a way of making itself known in the sky. Now I'll hand it over to Dev to introduce our speaker for tonight.
Thank you. Hello, everyone. My name is Dev, and I'll be introducing our speaker, Rosayla Coulthard, today. Rosayla Coulthard is a second-year student at the University of Toronto pursuing an astronomy and physics specialist, statistics major, and mathematics minor. She's currently doing research with Dr. Tingley's research group at U of T. Their work refers to astrostatistics, stellar streams, stellar chemistry, machine learning, and dwarf galaxies. Some of her research interests include stellar physics, astrostatistics, big data application, and astronomical instrumentation. Welcome, and thank you for being with us, Rosayla.
Thanks so much for the introduction and for everyone at the Allen Carswell Observatory for giving me this opportunity to share some of what I've been working on. Before I start, though, hope everyone can see my screen. I just want to take a moment to thank my supervisors, Dr. Nathan Sanford and Dr. Tingley, as well as the rest of Dr. Lee's research group and the DESI Milky Way survey group for their feedback and guidance on this project so far. And additionally, thank you to the funders of this project. Yes, so like Dev mentioned, I'm going to be talking about machine learning and some of its applications to astronomy, and in particular, its application to stellar spectra. So machine learning is one of those buzzwords right now that you hear thrown around a lot, but it's for good reason. Machine learning is quite versatile and it can be applied to a lot of different fields because of how good it can be for pattern recognition. And in the case of astronomy, it can help us improve the quality of our data and help us see patterns in that data that we wouldn't have otherwise spotted. During the creation of these machine learning models, the last stage is data validation, where the predicted data is compared to some testing data set. And this last step is what my research has mainly been focused on. But before I talk about any machine learning model stuff, I want to give a little bit of background information about stellar spectra and why we're making these models. So the light that we observe from a star contains information relating to the star's composition in the form of stellar spectra, which we can acquire using a spectrometer. Dips in the spectra at certain wavelengths called absorption lines can indicate the presence of certain elements in the body that emitted that light. And since each element has unique absorption and emission line patterns, we can use the spectra to assess the composition of the star that gave us that spectrum. So to measure the quantity of how much of an element a star will have, we can use a relative solar scale to compare the amounts that we measure to our sun. And this is done using decimal expansion units. So for instance, if we say that the magnesium abundance of star X is -2 dex, we're saying that it has 100 times less magnesium than our sun. And additionally, every element is also measured in its relation to iron. So for example, the magnesium abundance is really the magnesium ratio to iron, except in the case of iron, where it's iron to hydrogen. And spectra can also tell us some other parameters about the star, like its surface temperature, radial velocity, and surface gravity. So this is cool and all, but why do we need this information? So the chemical abundance and kinematics of a galaxy's stars can help us better explore topics like galactic evolution, star formation, the enrichment of the universe with heavy elements, and the nature and distribution of dark matter. So for instance, the redshift of galaxies can reveal information about their distance. Their radial velocities might suggest nearby structures, and composition can help indicate what, if any, types of dust are nearby. In particular, we're very interested in the stellar spectra of stars in dwarf galaxies surrounding the Milky Way. Dwarf galaxies are smaller satellites of the Milky Way and are some of the oldest, most dark matter dominated, and least chemically enriched galaxies, and thus provide a unique window into the astrophysics of the early universe. Many galaxies will form through the accretion of smaller galaxies through merger events, so dwarf galaxy physics will also provide insight into these larger galaxies. The composition of stars can also indicate the events that led to a star's formation. If a trend appears among a group of stars, for example, we can conclude that that group of stars all likely formed from the same process. And we can sort of conclude this through various different kinds of groups of elements, which all indicate different formation events. So for example, alpha elements like oxygen, magnesium, sodium are produced in the core collapse of other stars. Iron peak elements like iron, of course, chromium, and nitrogen are produced in white dwarf explosions, which can happen over a longer time scale. S-process elements like strontium, yttrium, and barium can come from the stellar wind of lower mass stars. And lastly, our process elements like europium, thorium, and iridium are produced in neutron star mergers. So a good example of how we can use stellar spectra to model galaxy evolution is through the use of radial velocities to support the existence of the Gaia Enceladus sausage. If we look at the radial velocities of the disk stars in the Milky Way, and we also look at their chemical abundances, you can actually notice that there's a noticeable subsection of stars with very different alpha element quantities. In this plot here, you can see the rest of the Milky Way here in black compared to the Gaia Enceladus sausage stars. And we can see that they're very distinct from the rest of the Milky Way stars. And so this in combination with kinematics helped us conclude that the sausage galaxy and the Milky Way collided about 8 to 11 billion years ago in a merger event. And the evidence that remains is this interesting stellar population with slightly different chemical abundances. So this is just one example of how we might actually apply this to understand how galaxies came to be how they are today. And so right now, there are many large-scale surveys that are collecting stellar spectra for stars within our Milky Way, such as LAMOST, Apogee, and Gaia. And I'll be focusing on one specific instrument, which is the Dark Energy Spectroscopic Instrument, which I'll be referring to as DESI, which is mounted on the Mayol 4-meter telescope at the Kitt Peak National Observatory. And so one of the many projects utilizing DESI is the DESI Milky Way Survey, which we can see the data distribution for here, if this loads. There we go. And it maps the thick disk and the halo of the Milky Way. It provides us with a lot of spectroscopic data. However, due to its low resolution, it can be hard to get specific abundance measurements from this data. So to work around this, many machine learning models have been made to predict specific chemical abundance measurements instead. As for the Milky Way surveys, some of the ones made so far include the SP pipeline, which derives atmospheric parameters like surface gravity and effective temperature, as well as chemical abundances. There's the RVS pipeline, which focuses on atmospheric parameters, specifically radial velocities, and the WD pipeline, which focuses on white dwarfs. So machine learning models will utilize the spectra to return specific chemical abundance or atmospheric parameter measurements. And so far, these three pipelines have been doing pretty well and have been predicting abundances fairly accurately. There's also many more models in development, all at various stages of development, and all which focus on different abundances or sets of stars. So currently, I'm working on helping test these models to determine how good their predictions are. But before I get into how I'm working with these models and testing them, I want to talk about a specific example of a machine learning model that was applied to DESI, since I think that this model and its validation is a good example of the process of machine learning and how it can be applied to stellar spectra. So the model in question is the data-driven pain model, which I'll refer to as the DD pain, which was applied to the DESI early data release dataset, which I'll call the EDR, to predict chemical abundances for around 500,000 stars. So the main premise of the DD pain model is that it's data-driven while still relying on underlying physics to map a set of stellar labels to some given spectra. Data-driven models focus on the data itself. It looks at the input, the output, and using whichever type of statistical modeling decided on, connects the two to create a method for determining labels, or in our case, for determining spectra. This approach is often better when there's a lot of data and patterns are not clearly visible, which is perfect in our case since we aim to apply these to as many stars as possible. However, the DD pain also relies on the underlying physics of stellar chemistry to make its predictions, which is what makes it different from traditional data-driven models. If a star, for example, if stars typically have X elemental abundance and not Y, the machine learning model will make an attempt to not say it has both X and Y, for example. So in addition to that, the DD panes expanded on other previous models' interpolation functions, making it more general, allowing for less restrictive label predictions. So overall, what it's doing is it's utilizing something called a multi-layer perceptron neural network of 2 hidden layers with 10 neurons per layer. And so the way neural networks work is they will send the data through all these hidden layers, through all the neurons, and at each step, they'll decide on the weights of certain coefficients in some function, which they're using to predict the output. In our case, since we're taking in stellar labels and outputting the spectra, it's predicting the coefficients for the flux to pixel function. where W and B are coefficient arrays, which need to be optimized. The index I is the number of neurons, and K is the number of labels. And then in the case where the model is applied to low resolution data, a loss function is implemented just down here. And these loss functions essentially measure how off predictions are from the real data. And the goal, of course, is to minimize this function. Yes, so recently, in a paper by Zhang et al. Just about a year ago, the model was applied to the DESI EDR to predict 12 chemical abundance measurements along with 3 atmospheric parameters for 520,000 or so stars. So the training sample for the DD pane applied to EDR contained 3,600 or so stars from cross matches of DESI and LaMost, as well as DESI and Apogee. Most of the stars in the sample were main sequence turnoff stars. They were mostly metal rich and located in the disk. And we can sort of see up here the distribution of the training data. It has pretty good range of data. It's got enough variety. And in the output data down here at the bottom, we can see that it output way more data than what was put in. But we can also see some interesting side effects of what the machine learning model produced. For example, down here, we can see that these low metallicity stars past -3 dex, that it's sort of sectioned off from the rest of the data. We can also see over here in the Kiel diagram this strange uptick that occurs at the end here, which normally doesn't occur. Small side effects like these are usually just due to noise errors or not having enough training data, so the predictions aren't as good and will have some funny features like that. But so to determine the accuracy of this model, what they did in the paper, they compared the DD pane EDR predicted data to the DESI SP pipeline data for the same set of stars. We know that this can pretty well tell us the rough accuracy of the DD pane, since we know that the SP pipeline is quite good and predicts well enough. And so looking at just the atmospheric parameters, we can see where the red line is the SP pipeline data, and the other points are what the DD pane predicted. You can see that it is fairly consistent. There's small deviations, but that's expected. There are still interesting machine learning side effects that we can see here, like these strange vertical lines, or how it gets very choppy here. But once again, these are just due to training data limitations, noise in the data, and of course, the slight variations. Overall, though, very consistent. We can also compare the predicted chemical abundance values with the apogee chemical abundances, which are here on the red line. And these plots are all of the abundances that the DD pane had predicted. And we can see that especially for these metal-rich stars, the red line overlaps with what the DD pane has predicted quite well. But the metal-poor stars, on the other hand, as we move to the left in these diagrams, were harder to determine because of the limited training sample. The paper actually chose to cut off abundances at a metallicity less than -1.5 dex for nitrogen and titanium, and metallicity less than -2 for other elements due to actually not having enough training data labels. And what's particularly interesting about all these plots is that they really show you how the model starts to break down when you look at the very extreme end of the data. Looking at any of these plots, you can see how as metallicity decreases, the density of the data also decreases, and it begins to scatter more. Especially over here, for example, with carbon, it just really explodes way at the end over here. It also appears that the red lines of the apogee data trend in sometimes the complete opposite direction of where the data seems to be heading. Like here it did for nitrogen. The data suggests it's going up here, but the red line is way down there. And this is, of course, by no means the fault of the model or by those employing it. It's really just the lack of metal-poor star training data. And given that large stellar surveys tend to sacrifice precision for volume of measurements, it makes sense that metal-poor stars, which tend to be harder to detect and more so out of the way, that the data for them would be lacking. We didn't look at it. Instead, we got as much as we could for other stars. So moving on to what my research is involved in, it's sort of fixing this gap in the models by curating a data set which contains enough metal-poor stars with low enough uncertainties to fill in the gaps in the testing data. I created the myself as well as a previous student, Shuhan, we created the Chemical Abundances of Metal Poor Stars catalog, or CAMPS catalog, which contains chemical abundance data for around 18,000 stars. The catalog as a whole has an average metallicity of about -1.6 dex, which is actually below where the DD Payne actually cut off predictions for a lot of their elements, which is really good. And CAMPS is actually, we didn't collect the data ourselves. CAMPS is actually a compilation of data from 312 papers, which specifically focused on these metal poor stars during their observing time, which works around that issue of larger surveys not dedicating enough time to non-disk stars. So to start, I want to spend some time talking about the inner workings of the catalog and the process involved in the creation of CAMPS. Big data and its applications to astrophysics is very messy and it's very intricate, but it's also very, very interesting. So I want to spend a bit of time talking about that. But first, like I mentioned, so the main structure of the code and the first bit of the code, which we'll talk about now, was created by a previous student, Shuhan. So thanks very much to him for being the foundation of everything. All right, so firstly, how are we getting all of this paper data? All the papers that have been added to the catalog so far come from the Strasbourg Astronomical Data Center from either the Vizier or the Simbad database. So whenever someone publishes a paper, they have the ability to add their data to this database, which allows for people to import that data directly into a Python file in the form of a pandas table for anyone who's familiar with that Python package. And for every paper that we want to add, we can specify some parameters that the code will then use to properly import and then manipulate the data from each paper. So we'll feed it the author name, the year it was written, which of the provided tables we want to use, and a unique code attached to each paper, which allows it to be searched up within the Vizier or Simbad database, as well as some other important parameters that we'll need. And what it returns is this raw data table straight from the paper. So then what the code will go and do is ensure that our data is usable. So that's to say that all data types in all of the columns are consistent with some established standard, the standard being right ascension and declination measured in degrees, and all data types stored as either strings or floats in the table's columns. Then to further clean the data, the column names of the table were changed to match an established column naming convention. The naming convention, along with some other necessary standardizing information, is stored away in a very, very long file, which we'll be using later. And for the given set of columns in the incoming paper, what the code will do is we'll check if these names are stored in our very, very long file. And if they are, the names are changed to what's listed. And if it's not, the code will prompt the user for what they want the column names to be, and then add those to the long file again. And so similarly, if the code recognizes that the incoming paper contains stars from a cluster or a dwarf galaxy that hasn't yet been recorded in our catalog, it'll similarly prompt the user for the correct spelling. What type of object is it? Is this a dwarf galaxy, a cluster? What is it? The code will also then standardize these names as well. And so keeping the column names, types, object names, everything like that standardized ensures that when we process multiple papers through the code, they can easily be combined into one data set all at the end. And once all that's done, the paper data is then saved. What I have up on screen now is an example of the absolute chaos that occurs when you try to clean a data table yourself. Half of the columns might need their names changed. Why is this column missing its data? We have two of the same columns here, but they're in different units. Sometimes we don't even need all of the columns. So having something to standardize this process is very nice, saves a lot of headache, and definitely makes the end result a lot nicer. So at this point in the compilation, we have some file full of nice clean data tables, one for each paper that we want to include in our catalog. Now what we want to do for each paper is to stack them on top of each other into one big catalog. Now, unfortunately, this is where I run into the most time-consuming issue of the project. So the joke about astronomers being bad at naming things is very fun when you first hear about, the Gaia Enceladus sausage or the Very Large Array or some other whimsical name. But when you're having to deal with the naming convention yourself, then it becomes a little less funny. So say you're stacking 5 papers that you cleaned into one catalog, but each paper decided to label their stars from 1 to n. Now when this paper's stacked, you have 5 stars with the name 1, 5 stars with the name 2, and so on. And even worse, these are all different stars, so their name really doesn't mean anything at this point. So to fix these inconsistencies in naming caused by everyone making their own naming convention, let's make our own naming convention. So the naming convention, which we will call star ID, has the form object underscore number, where the object is whatever dwarf galaxy or cluster the star is part of, and then the number is some unique integer that we've given to that star. And so to determine which stars are unique, as we stack each paper on top of each other, we'll cross-match that incoming paper with what we have already stacked. So for some star in our incoming paper, we'll perform a cross-match between that star and what's already compiled with a separation criteria of 1 second, which is to say that for this star, let's construct a 1 arcsecond radius around it. And if there's another star within the 1 arcsecond radius, let's consider them the same star. And if it's not within the radius, we'll consider them different stars. This sort of ensures that if 2 stars are the same between 2 different papers, our catalog will say, oh, look, this is the same star. These should have the same name. And so if we do find a match, they'll get the same name. And if the star has no matches, it'll get given its own new star ID. And of course, once again, as we stack all the papers, we also have to clean the data again. So you can sort of see here in this screenshot on the right from a sample of the table, these stars very obviously are the exact same star. These measurements are ridiculously close. They even have the same name. Well, almost the same name. But if we were to use this data as is, without giving them the same star ID, the catalog would say that these 2 stars are the same star and that this third one is a different star, which you can see is very much not true. These have the almost exact same coordinates in the sky. And so generally, this is how the CAMS catalog is compiled, but it can work for really any set of papers. It doesn't just have to be papers that focus on chemical abundances. So this method of compilation would work for any columns you feed it, really, because you're specifying the names that you want in that very, very long file, and that's user dependent. So one last thing relating to the compilation of CAMPs that I want to mention is that the concept of a literature catalog isn't new, and it's been done on many instances before, for example, with Saga or with the Genabase and other small catalogs made by individuals. But what is new about CAMPs is that it's a living catalog, and you can add as many papers as you like because the code will recompile a new catalog for you with each set of papers you feed it. And so to not sort of discard the other work that was done to compile previous literature catalogs, there's a key component to CAMPs, which is the ability to also stack those other compiled surveys on top of your manually compiled papers. So there's an option to add Saga, there's an option to add the Genabase, and a third catalog by Alex G, which focuses on the chemical abundances of dwarf galaxies. Okay, so with the technical side of CAMPs done, let me cover some of the more interesting parts of CAMPs, which is what exactly the final result is. So the catalog contains data for all of these abundances, as well as these atmospheric parameters listed down here. Interestingly enough, it does contain various ionizations of certain abundances, which can be a little confusing, especially because some papers will specify which ionization state they're measuring and some won't. But all of the species were left in just to try to not box users in too much into what they want to do with this data. It also becomes very apparent which papers are using which ionization level if you actually go and look at the data and sort it out. And other than these, the catalog also contains various other columns, which are for, I guess you could say, administrative purposes. So we have, of course, right ascension and declination. We have the paper that provided the stars. We have Gaia ID, which is that star's corresponding ID in the Gaia surveys. We have the name of the star, which is the name the author gave it, not to be confused with star ID, which is the name I gave it. It also has object name, which is the name of what celestial object the star belongs to. Object type, which is the type of that object. And lastly, to actually utilize the whole star ID, all you would do is sort by unique star ID, and there is your unique catalog. And the catalog itself, like I mentioned, just over 18,000 stars from 312 papers from various different sources. Now, what's interesting is that if you actually were to sum all of these unique stars, you would get way more than 18,000. And sure, these are unique stars among the catalogs themselves, but among each other, they're not necessarily unique. So you can see just the sheer difference in magnitude between just stacking them and actually tracking which stars are unique has its big difference, which is why we need to make sure we're using that star ID. The difference is large enough so that if we were to use this data and not pay attention to which stars are unique, it might suggest trends in our machine learning models which aren't necessarily accurate since we're looking at the same star 5 times, for example. So visually, among the manually compiled papers, we have an average metallicity of about negative 1.75 dex, and then among the whole catalog, we have an average metallicity of about negative 1.61 dex. You can see here in the histogram on the left that the distribution is quite good. We have most of it being below 0, so most of the stars in our catalog are more metal poor than our sun. As we go down to even like about -4 metallicity with good enough sample size, which is fantastic for a catalog of this size. And as for the nature of the stars in the catalog, there's also a good distribution with a bunch of different stars along different points in their life cycle, which you can see here in the Keel diagram. But yes, so with this variety and flexibility, CAMP sounds like a pretty good tool on paper for validating machine learning models. But let's see an actual example of how we can apply this to validate a machine learning model. So going back to the DD-Pane, let's compare the CAMPS catalog with the DD-Pane predicted data. So to do so, we perform a cross-match between CAMPS and the DD-Pane predicted data with a separation criteria of 2 arcseconds. And for every star that's in common between the two, we can plot the differences in their abundances over their metallicity. Now here we're actually using an arcsecond separation criteria of 2 as opposed to 1. This is just so that we can maximize the number of cross matches we get while still maintaining good enough accuracy. Here on the left, we can see the differences in predicted metallicities between what CAMP says and what was predicted. If, in theory, in a perfect universe, all of our machine learning models were perfectly accurate, we would expect all of our points to lie on this horizontal line. This line, unfortunately, is very far from horizontal. It does suggest that what was predicted is linearly off by what seems to actually be true. And it's not just one star that says this, it's a whole bunch of stars. Unfortunately, as well, being off by a magnitude of 1 decimal expansion is quite significant when it comes to working with numbers that are this small and are on a logarithmic scale. But of course, we can't have it all. If we look at other elements, for example, if we look at the difference in carbon abundances, we actually really only get 1 point, 1 data point. And that's because all of the papers that we've compiled don't all necessarily have the abundances that I listed before. So out of our, I believe it was 48 cross matches that CAMPS had with the DD-Pane, only one of those actually had a data point on carbon. And the data point is also showing that it's very good. So obviously, we've run into the same problem that we had before, which is that there really isn't enough data on these metal poor stars. And so, despite me saying that large stellar surveys can't always account for low metallicity stars, that doesn't mean they're awful. Large surveys are really good for validating machine learning models. So in the case where this happens, we can also apply other methods of validation, other data sets. So if we cross-match the predictions with the most recent Apogee, Lamoste, and Gala data releases, our comparisons start to look a little bit more reasonable. Once again, we do so with a separation criteria of 2 arcseconds. And when we do this, we can see that the limited CAMPS data points that we do get actually do agree with what these other stellar surveys are saying, which is great. But we can also see how the DD-Pane is performing. For example, looking at carbon up here, for the higher metallicity stars, it's fantastic. Looks quite spot on. But as you start to decrease and we start to go past the cutoff that was established in the paper, it really starts to scatter a lot. Even more so for something over here, like chromium, it's way off, it's so scattered. These plots are also very interesting because they also exhibit side effects of machine learning, which is, for example, down here, going back to carbon, this weird subsection of data that's appeared here. Now, anytime you see anything like that in machine learning models, it's usually a sign that something is funny with your training data, and it's just a lack of it's pretty much just this data set, this set of stars wasn't in your training data, so the predictions are a little bit off. But other than that, definitely, especially below even -1, most of the elements begin to scatter way too much. So the DD pane, of course, is just one example of a model that CAMPS can be applied to. We have other models being created right now that we're working on validating. Something that I think we should keep in mind when using CAMPS to validate is that the data in CAMPS comes from various sources using various instrumentation, all of different ways of handling their data. So we should focus instead on the overall trends that CAMPS tells us instead of specific numbers. In the future, CAMPS definitely has room to grow in this regard. We can, for example, standardize solar scales between all of the papers to get things just a little bit more precise. We can also maybe provide quality flags on the papers that are coming in. But for now, CAMPS serves its purpose in just looking at overall trends. So to summarize everything that I just mentioned, stellar chemical abundances can help us figure out the events that led to star formation. And when done in bulk, we can look for patterns among these abundances to potentially figure out how a particular cluster, for example, might have formed. And on an even larger scale, we can hopefully use this to uncover the formation of our galaxy as well as others. To get our data to do this, we rely on large-scale stellar surveys, which will often take lower resolution measurements in exchange for volume of measurements. But this resolution problem can be overcome with machine learning models, which work great until we start looking at metal 4 stars, which we tend to have less data for. But hopefully with the creation of catalogs like CAMPS, we can more accurately assess the accuracy of these models for these metal 4 stars and just make better models overall. Yes, that's all. Thank you.
Thank you so much, Rosayla, for that very fascinating talk. Now, if you don't mind, we have a few questions for you. The first question is from Zach.
Hello, I'm Zach. I'm a second-year astrophysics student here at York, and my question is, how can we detect and mitigate biases in the training data that might lead to incorrect chemical abundance predictions?
Yeah, so this is actually a really good question, and it is a problem that we will continue to run into with machine learning models, simply because the models will always predict based off what we feed it. So the best way to work, I guess, to improve the bias that we might encounter is to make sure that our training sample is very diverse, very random. We want to make sure that we're using really good quality data. So if the data is fuzzy, it will predict as well since it's not quite as certain as what's going on. Something else we could do is also to flag data that we're using. So we want to make sure not to use any suspicious measurements. If we throw in an outlier, for example, that might just throw the model way off. I guess another way to overcome some biases would also just be to employ the underlying physics of the model that we're trying to make. If we know that stars that usually have high abundances of X don't tend to have high abundances of Y, we can make sure in our model that we're not seeing stars that have high abundances of both X and Y, since that wouldn't really make any sense.
I see, thank you. And my next question is, in what ways might a machine learning model struggle when applied to stars outside of the dataset it was trained on?
That's also another good question. I guess that also relates to if the training data is biased, if the training data is biased, then the model that we have will predict the abundances potentially incorrectly for stars outside of the training data. And we actually kind of sort of saw this with the DD Payton model. It would just sort of put a whole chunk of the stars well below what the other ones were being predicted as. Ideally, a good model won't care where the data's coming from. If it's a good model, it won't be too overfit to the input data and should rely on enough underlying physics, for example, or a well-trained enough function to accurately predict for stars outside of the training data set. But it definitely does struggle with that, and that's sort of what we're hoping to trying to mitigate with things like camps.
I see. Thank you so much.
Now we have a question from Darius.
Yes, hello, my name is Darius. I'm a fourth year astrophysics student at York. And my question is, are there stars in the database that come from beyond our galaxy or just within the Milky Way?
Yes, so all of the stars right now in camps are from the Milky Way. I think there's an exception of a few of them. Right now, we're applying all the data that we've collected to Milky Way data, so it makes sense for us to look at just the Milky Way stars. That's not to say that it can't be expanded, especially if we're ever using a model that predicts abundances for stars part of other galaxies or other objects that are further away. The catalog can definitely be expanded to contain other sets of data and other sets of papers. But yeah, so for now, it just contains Milky Way since that's sort of what we're hoping to use it for.
Interesting. Okay. My second is to ask, what other astronomical fields of study do you believe that machine learning could help us make progress in?
This is a good question. I like this one because it's very machine learning is definitely like a buzzword right now, and everyone's sort of hearing about machine learning this and machine learning that. But it is very good to work with anything that is data related. So anything with massive data sets or that use basic class that rely on basic classification and basic pattern recognition. It's very good for those. And there's a lot of that in Astro, especially anything observational. So it could be used, a good example, I guess, is to find transients. If we're constantly monitoring the light from some star or from some object, we can sort of check for any sort of patterns using machine learning models in this data that we feed it to check, is something actually passing in front of the object here? Another example is similarly exoplanets. We can find that way, and machine learning can be applied to that, for example, by just I guess properly looking for patterns within the data. It adds an extra layer of, am I actually seeing something here?
That's very interesting. Thank you for a great talk.
The next question is actually for me, and it's why is it important to study metal poor stars and what can we learn from them?
This is a good question. So metal poor stars are particularly useful for modeling galactic chemical evolution because of their old age and when they were formed. A lot of them are from way before a lot of the more younger metal-rich stars are. So they act almost like fossils from this earlier age of the galaxy. So by looking at these metal poor stars and figuring out, oh, look, all of these might have formed in this event, we can sort of go even further back along the cosmic time scale and potentially look back into like even the formation of the Milky Way right at the start, potentially. Also, it has a lot of dwarf galaxies will have more metal poor stars. The outer parts of the halo will just have more metal poor stars than the disk generally. And the dwarf galaxies are very dark matter dominated compared to the rest of the galaxy. So they can be particularly interesting in that regard.
Okay, that's really interesting. My second question is, what were some challenges that you faced while dealing with such large data sets?
I think I think the biggest challenge is that joke about astronomers being horrible at naming things. Um, when dealing with large data sets, especially from different sources, everyone sort of has their own idea of the best format. And then another person will look at that format and go, wow, that's a horrible format. I don't want to use that. So the biggest challenge was definitely standardizing everything. A lot of different columns will hide their data, for example, to reduce risk of corruption, but then it makes it a pain to unhide it. Some other tables will have their stars on the y-axis instead of the x-axis or vice versa, and it's just a matter of standardizing everything and cleaning it and then getting it to work that I think was the hardest part.
Yeah, that makes a lot of sense. The next question is from Zed.
Hello. I'm Dev. The question which I have is, can machine learning model predict any major space events such as supernovae or black hole formations?
So this is interesting. I suppose in theory, a machine learning model could predict some major events, but it would really only do so because the model would provide us with a certain set of data, and we would then from that use physics to infer, for example, when a star is supposed to go supernova. So machine learning, at least as it tends to be applied to astro, it's best for looking at data that we already collected and then drawing patterns from that. As for inferring things from there, I think it mostly just depends on our own physics that we do already know. But I'm sure there's probably definitely research in that right now.
All right, very nice. So next up, can machine learning identify the probability of star formation in specific regions based on data?
Yeah, so machine learning can definitely help us get enough data to be able to draw conclusions like that. I'm sure in theory a model could give us a rough likelihood estimate of a region being a star formation region. But that of course would be based on the data that we're giving the model, what the model thinks of the data, and then the physics that we know so far. Sort of like how we can use the chemical abundances to predict what events have led to a star's formation. We can use the models to improve our data, but really only using our underlying knowledge of physics can we decipher what this data actually means.
Okay, so basically you have to have the input data to like predict these things, right?
Yeah, you have to have the data and then also the knowledge of what exactly is going on to know what this data could tell us.
Okay, okay. Thank you.
And our next question is from Hector.
All right. Hello, Rosayla. I'm Hector. Nice to meet you. And thank you so much for providing this truly interesting talk about machine learning with stellar chemistry. Absolutely impressive. The models and analysis were pretty interesting to see and learn about. Now, my question is, do you think machine learning can eventually replace traditional spectroscopic analysis, or will it remain as a supplementary tool?
This is a good question. I think this is definitely something talked a lot about as machine learning and artificial intelligence sort of expands as a field. I think I think we need to be careful since ultimately it's the physicists behind the models, making the models, analyzing the data that it gives. So I think because we still need to understand what the data means and then draw physical conclusions from that, it's likely just going to be a tool, at least for now. If it does, for example, in some spectroscopic analysis, notice something, we would still need to go further with what that tells us. And that's not necessarily something that the machine learning model would be able to do. But I think it definitely is like a very good tool for improving our data and working around some more, I guess, hardware issues, low resolution kind of issues.
All right, very interesting. Thank you so much. And yeah, I absolutely agree. I think that as a supplementary tool so far, it is doing a good job so far as we have seen in the models. And yeah, that yields to our next question. Well, my next question that is, how do you see machine learning shaping the future of stellar chemistry research?
I definitely think it has the potential to be a very useful tool. It lets us access large amounts of data all at once, which of course is always good for trying to come up with general theories and understanding of things. Um, it definitely does require more testing though, as you saw, since sometimes models just don't like to work for certain groups of stars. Sometimes there's funny patterns, but I think it definitely has the potential to shape the future of stellar chemistry in the sense that it expands the amount of data that we can work with and thus help us draw more solid conclusions based on the fact that we've got larger samples.
All right, excellent. Thank you so much, Rosayla.
Okay, that concludes the Q&A portion. And I will hand it over to Zach now to lead us out.
You have been listening to the Alan I. Carswell Observatory's monthly TeleTube broadcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Denelle, Hector, Darius, Dev, and myself, Zach. Make sure to leave any questions in the video's comments section or ask them in our live chat. We will be around for the next 20 minutes to answer your questions. All of our programs are free, but if you would like to donate to our observatory, please see our website at yorku.ca/science/observatory. You can always connect with us on Instagram with the handle @YorkUObservatory and check out our website for show notes, content, updates, and contact info. Thank you for tuning in, clear skies, and have a good night.